Hello, in this video I'm going to cover section 10.3, Triangles from Contemporary Mathematics by OpenStax. The learning objectives for this section are to identify triangles by their sides, identify triangles by their angles, determine if triangles are congruent, determine if triangles are similar, and find the missing side of similar triangles. Triangles are classified by their angles and their sides. All angles in an acute triangle measure less than 90 degrees. One of the angles in a right triangle measures to 90 degrees. And one angle in an obtuse measures between 90 and 180. Sides that have equal lengths are indicated by the same hash mark. And what that means is, if we look at this picture of this triangle, hash marks are like those lines that indicate, and so all of them are the same. That means they have the same, all the sides here would have the same. So a few other facts to remember as we move forward is that the points where the line segment meets are called the vertices, or the singular. Oh no, that's right. That's the plural for vertex. Sorry, thought that was a typo, but yes. Vertices is the plural for vertex, and we often refer to sides of the triangles by opposite angle, and it's lowercase. So for example, let's say we had this triangle and we called it ABC, and we use this notation, triangle ABC. Then we would say side A is a little a across from big A, side B is a little b across from side B, and little c is across from little c. So we name them with A, B, C, D, E, F. Letters, capital letters are vertices or angles, lowercase letters are sides. So triangles are kind of classified into different based on whether they have based on their angles or their sides. So we talked about the angles. Acute triangles are triangles who all of their angles are less than 90 degrees. So for example, a 60-60-60 triangle, if all of them were 60 degrees, that would be an acute triangle or something like that. Now the degrees of a triangle, and this is important, the degree of a triangle, should be an A in there, must add to 180 degrees. And there's a really awesome reason for that I will talk about in just a moment. But you have an acute triangle. A right triangle is a triangle where one of the sides is a right triangle, and the side opposite of the right triangle has a special name. It's called the hypotenuse. And then an obtuse triangle is one that has an angle that's greater than 90 degrees. So if it's greater than 90 degrees, then it is an obtuse triangle. Now, if we look at classifications based on their sides, then we have what's called an isosceles. And so isosceles triangles are ones where two sides are the same. So that's indicated by these two hash marks on this side, and these two angles are the same. So this is an isosceles triangle. Two of its sides are the same. An equilateral triangle is one whose all the sides are the same. So equilateral means all the sides and also all the angles are the same. So that's equilateral. And then we have scalene, which means that none of the sides are the same. So you can see here that we have three different hash marks. And so here we would have two hash marks for the isosceles on that third non-equal side, but in a scalene, all three of the sides are different. So we want to add a special note about right triangles. They're referred to more than any other triangle. In fact, what we know is trigonometry, right angle trigonometry, is all based on right triangles. So the side opposite of the right angle in a right triangle, as I said, is called the hypotenuse. Okay, so it's called the hypotenuse, and I can do a little better at spelling that. So hypotenuse. And these adjacent sides are called the legs. And one thing that's really not mentioned, but it's probably because you learned it in like middle school or early high school, is something called the Pythagorean theorem, which says that if we had this triangle ABC, and this is little a, this is little b, and this is little c, then a squared plus b squared equals c squared. Now, this is not the best way to put it. It's really leg squared plus leg squared equals the hypotenuse squared, because it's always equal to the hypotenuse squared, but we kind of shorten it as a squared plus b squared equals c squared, just for easier to say. So let's look at one of those algebra examples like we looked at in the last video. So as I said previously, all the angles inside a triangle must add up to 180 degrees. So what that means is x plus 17 plus 3x minus 62 have to add up to be 180 degrees. So we begin by combining like terms. So that's going to give us 5x. And then we've got negative 62 plus 17. So that's going to be negative 44 equals 180. And so again, that one-step type of linear equation, we add 44 to both sides. So we get 5x is equal to 180 plus 44, which is 224. And then if we divide by 5, that's going to give us x equals 44.8. And so if we plug x back in, we get 62.8 for this, 44.8 for this left-hand angle, and 72.4 for this other angle here. And if we add all those together, 44.8 degrees plus 62.8 degrees plus 72.4 degrees, that ends up equaling 180 degrees. So that is the measure of each angle, would be those 4 angles. And notice how they're all different. This is technically a scalene triangle, because if all the angles are different, all the side lengths will also be different. So let's look at this example. This is going to use some information from the previous section in order to solve all of these missing angles. So in the last section, remember, we had supplementary angles, and so if we're missing one of these angles, we know that the 2 angles in a line add up to 180 degrees. So, and then all the angles in a triangle also add up to 180 degrees. So to find this missing angle, we would do 180 degrees minus 30 degrees minus 89 degrees. And so that gives us a total of 61. So this is 61 degrees. And so angle 1 here is supplementary to 61 degrees. So if I do 180 minus 61, that tells me this is 119 degrees. Now 2 I get for free. I could have went ahead and said that because these are vertical angles. You see right here, this makes this V, so they're vertical angles. So that's 61 degrees for angle 1. I'm going to come over here to make sure I'm keeping track of all this stuff. So the measure of angle 1 is 119 degrees. The measure of angle 2 is 61 degrees. So we can't find 3 and 4 yet because we have 2 missing angles. We really need to only have 1 missing angle before we can make the leap to find them. So let's jump over here and we can find angle 5. Because again, this angle with this in this triangle next to 134 degrees is going to be supplementary with 134 degrees. So we're going to do 180 minus 134. So that's going to be 46 degrees. And so again, these 3 angles add up to 180 because they're in a triangle. So that means that measure of angle 5 is going to be 180 minus 46 minus 75. So that's going to be 59 degrees. And because 5 and 4 are vertical, that means 4 is also 59 degrees. And now we can finally figure out number 3, because that's in a little triangle, so that's going to be 180 minus 61, which is angle 2, and then minus 59, which is angle 4, and that's going to be 60 degrees. And so knowing all that information allows us to find all the angles in there. So another interesting thing about triangles that is often studied in geometry is the idea of congruence triangles, or congruent triangle, or congruency. And 2 triangles are said to be congruent if they are equal triangles. So if you rotated this triangle and then placed it on top of each other, so A, B, C, if you rotated it and placed it on top of D, E, F, they end up having the same shape and the same size. And that's what we mean by them being congruent, is that they have the same shape and the same size. And the way we write that is we say triangle ABC with this equal and a squiggly line over it, or a tilde. So triangle ABC is congruent to triangle DEF. So that's what we mean by they're congruent, is they are the exact same shape and size. So is triangle ABC congruent to DEF? Well, they are in fact congruent. So if we look over here, triangle A and C are congruent to angle D and F, which implies that angle B is also congruent, so to F. Because think about it, if these 2 are the same, right, and everything adds up to 180, and these 2 are the same and everything adds up to 180, then that means B and E have to be the same for them both to add up to 180. And we're given that AB and DE, as well as BC and EF, are the same length, right? And so what we basically have is all the sides and all the angles are the same, right? So all the sides and angles are equal. So these 2 must be the exact same triangle. It's just DEF has been laid over on its side. Well, what are some hard rules for this? And see, there's that symbol for congruency, is we have what's called the congruence theorems. And so if 2 triangles match in this way, and I'm going to talk about what those ways are, then you are guaranteed congruency. And those are as follows. So side, side, side. So if all the sides are the same, then those 2 triangles are congruent. Okay? And then we have side, angle, side. And so if you've got 2 sides and an angle in between them that are the same, then those 2 triangles are also congruent. We also have angle, side, angle. So if you have 2 angles with a side in between them that are the same on 2 triangles, then those 2 triangles are said to be congruent. And then the last one is angle, angle, side. And so if 2 angles and a non-including side, which you mean angle, and then there's not a side in between it, but you got a non-included side, then those triangles are said to be congruent. The only one that really isn't represented is side-side angle, right? So this is not congruent. All right, that is not congruent. So let's look at this picture. So what congruence theorem is illustrated here? So we've got two right angles. Okay, we got two right angles, and we've got this angle, which if we look, it's not easy to see, but if we were to draw these out and then draw this transversal line here, these two sides are parallel, so that means this is also the same, right? And so these two are the same, this angle and this angle and this side. So you've got an angle, and a non-included side. So that's angle, angle, side, right? And so you've got an angle, and you've got a non-included side. So these two triangles are congruent by angle, angle, side. You've got two angles that are next to each other, or in kind of in order, and then a non-included side. So that gives us angle, angle, side congruency for these two triangles. And if you wanted to, it's also sometimes helpful to break them apart to look. So this is angle, angle, side, and then the other triangle looks like this. And this is not drawn to scale, right? But you can see here we've got angle, angle, side, right? Angle, angle, side. That gives us that congruency. So another thing that we use to compare not just triangles, but triangles are powerful, but in general, and especially in graphic design and arts, is something called similarity. So if you have two kind of images and they are similar, we'll talk about what it means to be similar triangles, but if they're similar, then what that means is one is really just a scaled version or a larger or smaller version of the other. So similarity means that they only differ in size. All right, so one is scaled up, which means that they're proportional to each other. And that amount in which they've been scaled is called the scaling factor, which is kind of interesting. So if you're familiar with anything in like 3D printing, when you 3D print something, it comes out, it superheats plastic and the plastic comes out. But let's say that you wanted to build a box in 3D, and then you wanted to print another box, with the same kind of shape, but you wanted to make it larger, right? Then you would want to scale it up inside of the 3D printing software. And that's often what, sometimes I have to do is, because I'd like to 3D print, and so I have to use a scaling factor to make it larger, or maybe even smaller. So if I have to print, if the file that I'm trying to print on my printer is large and I need to make it smaller, then I need to use a smaller amount. So if a scaling factor is larger than 0, or sorry, greater than 1, not larger than 0, they all should be larger than 0. But if it's greater than 1, this is going to increase the size. Right? So like if you multiplied the height by 2, then you've doubled the size. That should make sense. It got larger. And then if the scaling factor is less than 1, but has to be greater than 0 because you can't do negative scale, something like 0.5, that means it's half the size, right? So an example here would be like 2 times, and this would be like 0.5 times, then you've made it half the size, so it's going to get smaller. So let's look at this picture here. There are two triangles shown. Notice how their angles are all the same. So angle, angle, angle we have here. This means that these two triangles are similar. But we haven't learned that yet. Another way we could determine whether they are similar is if the sides are proportional to each other. So what I'm going to do is I'm going to rotate this picture so that it looks like the other picture. So we've got this side And then we've got this, well, let me try to make it as close to scale as possible. So this is the longer side, this is the shorter side, and this is the hypotenuse. So if we take the ratio of the sides, which basically says like 4 and 2, so if we do that, if we do 2 over 4, and I need to write that, 2 over 4, which is a half, what happens if we do the next side? So that was side, we'll call this, let's label this triangle. This will be A, B, C, and this will be D, E, F. So this is the ratio of AB over D, or sorry, I got those backwards. So this is DE over AB. And then what if we do EF over, and then that would be BC. So EF is 3.5 divided by 7. So what's 3.5 divided by 7? And that is 0.5. So you see they have the same scale factor. And then now let's do the hypotenuse. So that would be DF divided by AC. And so DF is 4.03 and AC is 8.06. So 4.03 divided by 8.06, that is again 1/2. So they all have the same scale factor. So the scale factor equals 0.5. In other words, this triangle is half the size. It's been scaled by a factor of 1/2. That means they're similar triangles. All the sides are just scaled by a factor of 1/2. So how can we use that same concept to solve these like mathy kind of word problems? So this is like one of your quintessential textbook math geometry problems. A person who's 5 feet tall is standing 50 feet away from the base of a tree, as shown in this figure. The tree casts a 57-foot shadow, and the person casts a 7-foot shadow. What's the height of the tree? So what I like to do is you have really two triangles, right? You have the big triangle and you have the small triangle. So what I like to do here is I like to break them apart. So I'm looking at, in fact, two separate triangles. All right. So this big triangle has a side of X, 57 feet, and whatever the hypotenuse is. We don't really care about the hypotenuse, honestly. And then the little triangle that makes up the person who's 5 foot tall casting a 7-foot shadow. And so they share an angle here. So these two angles are the same. They're both right angles. And so that means that, you know, if these two angles 90 minus some other, that means that this third angle must also be the same. So that gives us another angle, angle, angle. And so if three angles are the same, then they are at least similar. And so these are two similar triangles. So I can do that ratio setup again. So that means that if I were to take, let's start with the little one, 5, and divide it by x, because this side is proportional to this side, because it's across from the same angle, and then equal to 7 divided by 57, again, because 7 is the smaller one across from the 57, and you have to make sure that the tops are the same and the bottoms are the same. So the tops were the smaller triangle and the top and the bottoms were the larger triangle. And then here what we do is we often do this process called cross multiplication, something you probably learned in an algebra class a long time ago. And so when we cross multiply, we get 7 times x, which is 7x, and 57 times 5, which is 285. And then we divide both sides, 57 times 5, yeah, 285. And then divide both sides by 7. That tells us that x is equal to 40.7. And this is in feet. So this tree must be 40.7 feet tall. And another way we could kind of figure that out is, if it's 5 divided by 57. So think about it this way. Actually, let's think about it this way. If we wanted to go from this little triangle to the big triangle, what does it take to go from 7 to 57? So 57 divided by 7. 57 divided by 7 is 8.1, we'll say 4. So that means the scale factor is 8.14. It's 8.14 times larger. So that means that it has to be 8.14 times larger than the man, or the person, sorry, it looks like a man, standing there. And so that's going to be, the height of the tree would then have to be 5 times 8.14, which actually ends up getting you 40.7 feet once again. So either way you want to think about it, if you want to think about it as ratios or proportions, or if you want to think about it as, well, what did it just take to scale up the triangle, they both get you to the same idea, because similar triangles is just a reinforcement of that idea of scaling factor. So that's all for section 10.3 that I'm going to cover in this video. There's so much more inside your book, so if you haven't already, read section 10.3. While you're reading, make sure you take those handwritten notes. That's how you learn mathematics, as you actually do mathematics. There are your turn problems within the section that I highly advise you work on and try for yourself. The answers are at the end of the section. And once you're finished with all of that, head on over to the LMS and complete your online homework assignments.